Assalamu alaikum, everyone. Welcome to today's class. So in the last class, we were discussing about the formulation of DC power flow, and later on at the later part of the class, we solved an example based on the DC formulation of conventional AC load flow. So the necessity of adopting DC load flow instead of the conventional AC load flow was because of the advantageous nature of the DC load flow, which helps us in speeding up the solution compared to the conventional AC load flow. However, one disadvantage associated with the DC load flow, as we mentioned in the previous class, is that we have to lose some level of accuracy in our result. So nonetheless, as long as we are not requiring very accurate result in load flow analysis, and at the same time, if we require very quick solution of the network load flow, so in those cases, DC load flow will help us immensely. So as we already know, the DC load flow formulation. So now in today's class, we will see that how the DC load flow concept can be applied for solving the optimal power flow, again considering the DC type of optimal power flow. So in short, we will call it DC optimal power flow. So before we look at the formulation of the DC optimal power flow, let us go back to the slide where we now show, this is the slide I'm talking about, the basic formulation of the conventional AC OPF. So when I say the conventional AC OPF, it means the OPF will take into account two things. One is the ELD. So we can write it like this. The OPF is basically the combination of ELD and load flow. So ELD basically will help us to optimize a certain objective. Load flow will provide us or will allow us to take into consideration of the equality constraints as well as the inequality constraints associated with the network. So by convention, we usually take the help of AC load flow analysis. So this term AC OPF means here the load flow is conducted with the help of the AC power flow. By that we mean, as we have already learned earlier, you have already learned different algorithms like Newton-Raphson algorithm or Gauss-Seidel algorithm or fast decoupled load flow algorithm. And all those things, when we adopt it for solving OPF or optimal power flow, then we will call it the AC OPF. So the formulation will look like this. We will have some certain objective, as we mentioned here. We will optimize certain objective. If our objective is ELD simply, then the conventional ELD, economic load dispatch. So in that case, this F is our objective function. We have a set of variables, U, X, and Y. So they have different names. You can find it in the previous lecture as we discussed in the class. Okay, so some variable will be state variable X, some variable will be the control variable, which is directly controllable by human intervention. X is those variables which we cannot directly control through human intervention. Y is a set of parameters which are assumed as constants or given, like the network parameters or the fuel cost function parameters and so on. And then we will subject the optimization to a set of constraints, some equality constraints. So equality constraints could be the power balance equations. So the power balance equation will belong to this set of equality constraint. By power balance, in general here, we mean both the P balance as well as the Q balance. This is where I'm talking about the AC OPF, remember, talking about the AC OPF. Then some inequality constraint. In the inequality constraint, we can set some constraints like line flow limits, S line, the reactive power flow, or sorry, the apparent power flow of the line, which can again be decomposed like the P of the line, real power flow limits, and the reactive power flow limits for the lines. Similarly, it can also be like the generation limits, real power generation limits, and so on. So the generation limits will be also a part of the inequality constraints. So as we said, Pi less than equals to the Pi max, sorry, Pi mean here, and Pi max over here. And also you can talk about the Q in the same manner. And also here we can include the VI, the bus voltage magnitudes. Similarly, the minimum limit as well as the maximum limit. So these are the, in general, the formulation of the ACOPF. Now, in this course, we are not going to discuss in detail of this ACOPF. So what we will do, we will simply take the assumptions as we discussed for the DC load flow. We will take the assumptions, and instead of considering the AC load flow, what we will do, we will take now the help of the DC load flow. And we will call the OPF as DC OPF instead of the AC OPF. So how will it look like when we formulate it mathematically? Let us see. So once we formulate it mathematically, it will look like this. So again, we will have an objective function, but now the objective function, in the objective function, our main goal or the main focus will be only on PG. There will be no QG, as we have identified already in the DC load flow case. Y is again the set of parameters. So this will be there because the network line parameters and the constraints like the generation, the cost function, associated cost function, coefficients of the cost functions, those will be known beforehand. So those will be constants, those will remain constant. So this will be the objective function. Now the variable of decision variable set will belong to PG, the generation, real power generation. And in the equality constraint, we only have to bother about the real power generation balance. So we have at a certain bus, we have PG, the generation, the demand could be there at a certain bus, and this is the bus power injection. And this is taken from DC load flow. So by now we already know what is B prime matrix and what is theta. So once you know the B prime and theta, this is basically my P injection. So overall, this line basically means that I'm looking for some balance at a certain bus. I'm looking for some sort of balance to be achieved. This is PG at a certain bus. This is P demand. So what is the, if I do it like a summing junction, so this is plus, so this is my summing junction, this is plus, this is minus. So output of the summing junction will be my P injected. For DC load flow, this P injected is nothing but B prime theta. So I'm looking for this balance over here in this equation. So that is my equality constraint. And remember again, we don't have to bother about the reactive power balance because it is DCOPF. And also again, this another set of inequality constraint is there. And in the inequality constraint again will be comprised of PG, theta, and Y. So there won't be any QG limit checking in this case. Only we will check the limits on PG. Okay, so now will all these are the constraints, equality and inequality respectively. So again, if we try to state the problem, we will state it like this, that we want to minimize the generation dispatch cost subject to the DC power flow equations. And if there is any other line flow and generation dispatch constraints, we also have to take into consideration. So this is basically the inequality constraint. This is basically the equality constraint. And we have this one, the objective minimization of that. Now, if we want, which we will not do, of course, in this course, if we want, we can extend this model to a more complex version of OPF that is known as the security constraint OPF. Security constraint OPF. But however, we are not going to take it in this course. Those who are interested, they can have a look at this later on. So now that we have this DC-OPF formulation, let us see how we can go for the solution for this DC-OPF. So in this course, the method that we are going to adopt for solving the DC-OPF, we will name it as the relaxation method. The relaxation method is already probably known to us, but by a different name. And if I specify the name at this point, probably you will be clear what I want to mean. The relaxation method will work similarly like some sort of, as we mentioned earlier, that is Kohn-Tucker condition. If you remember, in the Kohn-Tucker condition, what we did, Kohn-Tucker condition we applied for ELD. So Karush-Kohn-Tucker basically. So KKT, Karush-Kohn-Tucker. So Karush. So in that method, what we did, if we remember correctly, we adopted some mu variables. Okay, and the mu variables were associated with each of the inequalities. So if there is any inequality like less than, there would be one mu introduced. If there were any inequality like greater than, then there will be another mu introduced, and so on. But what we did to start the problem of ELD using the Karush-Kohn-Tucker condition, the first step was we assumed that there is no limit violation. There is no limit violation for any of the inequality constraint there. So to start with, what we did, we considered that all mu i's were 0. So in a sense, we can say that we relaxed the approach. We relaxed all the constraints present in the actual problem, and we tried to solve the problem. And we later on checked back whether the solution that we obtained after considering all the mu i's equal to 0, whether the solution violates any of the limits associated with the mu's. Okay, so if any of the limits were violated, what we did in the next iteration or in the next trial, what we did, we fixed these mu values. Okay, we made these mu values non-equal to 0, not equal to 0, and we again try to solve the system and so on. This is how we proceeded. So similar thing we will do, and similar concept, the generalized term, we can term it as the relaxation method. Okay, so I'm not going to go into the detail of all this. Basically what we are going to do, when we are going to solve one example, and there we will see what is actually meant by the relaxation method for solving the OPF. So let's proceed. So again, this is, I'm not going to discuss in detail. This is okay. So this is associated with our problem of OPF. So let's go through the basic procedure here. The basic procedure is, first of all, we will do the ELD solution. Remember, I said the OPF is nothing but, specifically the DC OPF would be then a combination of ELD plus DC load flow. This is what is DC OPF. And in the, whilst trying to solve it, there will be some constraints, of course. So the relaxation method means, the successive relaxation method means, to start with, we will ignore all the network constraints. Okay, all the network constraints. And if it were a security constraint problem, then all the contingent states, because we are not considering the security constraint issues. So do not bother about this term for the time being. We are focusing on this only. So first of all, we will solve an economic dispatch, assuming that none of the network constraints are violated. By network constraints here, I mean the P line. Okay, because in the DC load flow, there is no Q line. So we are on, our only focus would be to check the violations for the P lines. Okay. So by ignoring network constraints, we mean that none of the P lines are violated. Again, for the DC load flow, if you remember, we did not allow the bus voltages to be varied. Okay, so the VIs were assumed to be 1 per unit. So there is no way in DC OPF that the limit associated with the VIs can get violated. So we don't have to bother about VI limit violation. We only have to bother about the P line limit violations. So by the network constraints here, we mean the line real power flow through the line. So whether the maximum limit of the line, maximum allowable limit of the real power flows are getting violated or not, this is what we are going to check. Okay, so after the first step, what we will do, then once we get the ELD, means ELD will give me the PGIs. Okay, if you remember, PGIs will be obtained. Once we get the PGIs of each of the generating units, present in my network, then I will be able to solve the line flows using the DC power flow equations. And once I get the line flows, I can check for the line flow violations. If there are any line flow violations, then I will have to correct it. So in this lecture, we will also try to focus on the procedure of correcting the line flow limits. Okay, the procedure of correcting the line flow limits or the line flow violations. This correction will be basically done with the help of the linear sensitivity factors. What are these factors? These factors are commonly known as generation shift factors or generation outage sensitivity factors. Another one is line outage sensitivity factors. But in this course, again, due to time limitation, we are not going to deal with these line outage sensitivity factors. I'm only going to discuss what is the generation shift factor or generation outage sensitivity factors. That will come later on. So for the time being, we will focus on the application of DC power flow for OPF, DC OPF. So let us see an example. So this is the network we are interested on. So we have again 3 bus. This is a 3 bus system. So we have bus 1 connected with a generator, bus 2 connected with a generator plus load, and bus 1 we don't have any load. Explicit load is not present here. At bus 3 we again have a generation plus a load, and you see that loads are presented by their real power consumption. Okay, there is no reactive power consumption data given. So it is a 3 bus system, 3 generator system, and it is a 4-line network. So by 4 line, between bus 1 and bus 2 there is 2 parallel lines. Bus 1 and bus 3 are connected by line 3, and bus 2 and bus 2 and bus 3 are connected by line 4. So now let's have a look at the data given. So the line data and the generator data, or these are the data set that will be given to you. So the line data, like the AC conventional AC load flow, we need to specify what is the base power. So in this case, the base power is the apparent power. It is 100 MVA. And the line numbers are given sequentially. The first column over here. XL, this is the line reactance. This is small x. X for the line. So you can say this is X12. This is line number 1. This is line 1. So this is basically X12. Then again X12. This is line number 2. Same parameter throughout the network. Then line number 3 is between bus 1 and bus 3. So this is X13. And then we have line number 4 between bus 2 and bus 3. This is X14. And this is the maximum limit we talked about in the previous slide, while we said that the network limit. So this column basically will give us the network constraints of P line max limits. Then we have the generator data. We have 3 generators. First generator, maximum, minimum demand and maximum demands are given. Second generator given. Third generators are given. And then the cost data. Okay, so in this case, just for simplicity of analysis, we have adopted a very simple cost function. Basically, this is nothing but a straight line going through the origin type cost function. So if this is CI, this is PI, this means we don't have any nonlinear curve, neither we have any constant part. Okay, so in general, our cost function would have been like this in an ideal case. If it is a quadratic function, it would look like this. So alpha PG squared plus beta PG plus gamma, where gamma is a constant. PG and PG square, these are multiplied by corresponding coefficients of the cost function. So this is for the quadratic case, but in this case, you see it is simply dollars per megawatt hour. So if you multiply this value with the PG, actual PG of the generating unit, which is in megawatts, so you will get the cost in dollars per hour. Okay, so we can say basically we only are left with this. In this case, in this problem, we don't have any nonlinear part. We don't have any constant part, only have a linear part going through the origin. Okay, so you can simply say the beta, these are nothing but the beta coefficients for the original quadratic cost function. So these are the beta coefficients. Okay, the beta coefficients. So the beta coefficients. Okay, so if we have a closer look at this, we can clearly see that the costs are ordered in a priority based. The generator numbers are given in a priority based, and the priority is set based on the cost of the unit. So the lowest cost unit is given the first generator number, second costliest unit is the second generating unit, and the costliest unit is named as the generator number 3. So these are the data given, and beside this, now what we have to do, we have got the data for starting the problem of DCOPF. So let us see. So now, as we said, we will adopt some relaxation approach. By relaxation approach, what we mean is basically this part of the sentence highlighted in red text. So we'll solve an economic dispatch while we will ignore any network constraints. And again, I mentioned that no contingency will be considered in this course. So we are only bothering about the network constraints, that is the P line max limits. So let's formulate the DCOPF. So we have to have one objective function. So again, the objective function is simply the cost function, fuel cost functions. So the table 2 from the previous slide, this table is basically repeated here just to help us in formulating the cost function. So this is our cost function. Simply, what is the cost function? 20 is the beta. So simply we can say the F is summation of beta I PGI I equals 1 to 3. So this is my cost function. Okay, where PGI is simply represented by GI. So we have dropped the P, capital P, but it means the same. G1, so basically you see we are not using P anymore. These are only G. So G means the real power generation in megawatts. Subject to some equality constraint, first of all. So equality constraint, as I said, summation of PGI I equals 1 to 3 equals P demand. Remember, we are not considering any losses in the line, because why? Because R is very, very less than XL. R line is very, very less than XL, so there is no real power loss. So transmission loss is ignored also in the DC load flow formulation or DCOPF formulation. So simply summation of generation of all the generating units should satisfy my demand. So this is G1 plus G2 plus G3 equals to 250. 250 is the demand given here. Okay. So how are we getting 250? Let us see. If we look at the network, original network, this network, so you see we have two loads. One load is connected at bus 2, and another load is connected at bus 3. So simply we add up the load demand. So it is 200 plus 50, you will get the 250 megawatt that is being used here. Okay, this is the 250 we are talking about. So this is the only equality constraint that we have to satisfy. Now we try to figure out what would be our inequality constraints. So inequality constraints, again, the inequality constraints family would be this PGI min and PGI max. Okay, so this is what we are looking for. So now we can see that G1, okay, G1 should be, this is the lower limit. So that means the generation of generating unit 1 should be greater than the lower limit. This is okay. This one is the upper limit. So we should have written it like this. However, the approach that we are going to adopt for solving the DCOPF in this course is the graphical approach. Okay, we'll see. The graphical approach will help us in many ways. However, it has certain limitations. A more generalized approach is the linear programming approach. Remember, the linear programming approach. However, in this course, we are not going to cover it. So the LP, in short, LP approach is the more generalized approach, which can deal with any number of generating units. The graphical approach can deal with only up to maximum 3 generating units because of the representation problem. Okay, for the 3 generating units, we can have a 2-dimensional assessment. We can have a 2-dimensional plane. We will see very soon while we will solve this problem. But if the dimension increases, the number of generating unit increases more than 3, then we have to deal with a 3-dimensional space, which is difficult, but it's still possible. However, if the number of generating units goes beyond 4, then it is impossible to visualize. So in those cases, we have to resort to the more generalized approach of linear programming. However, for a smaller number of units, graphical approach is more convenient. And of course, for the exam purpose, it is solvable within the given allotted restricted time duration. Okay, so that's why we are going to adopt the graphical approach in this course. So in the graphical approach, what we will do, we will reform the given constraints like this. The less than equal to constraints will be converted to the corresponding greater than equal to constraints, all of them. So while we will find anything like this, we can simply change the sign of this inequality, and at the same time we have to take care of the signs of the associated things appearing on either side of the inequality sign. So this is how we are going to change it or update it, so that you can see now that all the constraints over here have been converted to greater than or equal to constraint. Okay, there is no less than equal to constraint anymore. But while we do this, we have to make sure that these signs are updated accordingly. Okay, so these are the constraints for the 3 generating units. So we have 3 generating units. Each unit has its own upper limit and lower limits. So in total, we will have 6 inequality constraints, and all of them are now converted to greater than or equal to constraint. Okay, so we are done with the formulation part. Now we will apply this formulation. We'll apply this formulation for solving this problem at our hand. So now let's look at the graphical approach. So in the graphical approach, what we will do, we will first figure out the cheapest unit. Okay, we'll try to figure out the cheapest unit first. So how we are going to do this? We'll simply look at the cost value. Okay, so and then we will pick out the minimum cost unit at first, and we will try to take the generation of the minimum cost unit as much as possible to satisfy the demand. Okay, this is our first priority. If not possible, then we will take help of the second unit. If not possible, then only we will take help of the remaining costlier units. So this is the sequence how we are going to solve the ELD manually, okay, without adopting any standard method of solving ELD. We are simply going to adopt this way to figure out how much generations are coming out from each of the generating units present from in my network, in our network. Okay, while doing this, we also have to take a look at the minimum generation, minimum generation possible for a certain unit. Okay, so if, let's say, if I want to say I want to satisfy a demand with generating unit 1 and 2, for example, then I have to make sure that at least I take this much from generating unit 2. Okay, if not more, because if I decide to turn on this unit number 2, then at least I have to take this 20. However, for generating unit 3, there is leeway. I can do with 0 megawatt also. Okay, so even if the generating unit 3 is running, I can claim that, well, I can take 0 megawatt even it is running, because that is allowed for the generating unit number 3 in this case. Again, for generating unit number 1, if it is running, at least I have to make sure that 100 megawatt is being taken, and so on. So now let's see how we apply it. Okay, so now, first of all, before solving the ELD, what we have to do, we have to find out the feasible solution space. Okay, the feasible solution space in this 2-dimensional plane. So if see what are the x's over here, what are the coordinates? In the x coordinate, we are putting G2 variable, decision variable G2, And the y coordinate, we are putting decision variable G3. However, you can swap them without any hassle, okay? Without any trouble, these two variables could be swapped. There is no issue. So let's see how we are going to solve it. If G2 is along the x-axis and G3 is along the y-axis, what about G1? G1 will not appear explicitly on this feasible solution space because that is our third dimension. So G1 will be implied, okay? Implicitly, the solution value, we will write it down with the brackets, okay? Just to ensure that it is there, but it is not visible in the 2D plane. So G1, 0 means it is our 0th trial or the first trial. Remember, I talked about trial. This is relaxation approach. So in the relaxation approach, we will go through trial and error. So this is our first trial. So that's why we are denoting the values by G1 subscript 0. Okay, this is our first trial. So in this trial, we are ignoring all the network constraints. That's fine. Already discussed what does it mean. Then we take the feasible solution space. What is the feasible solution space? How much we can take minimum from G2? Minimum G2 I can take is 20. So this is the limit for G2. Okay, let's check again. The minimum I can take for G2, generating unit 2 is 20. Maximum I can take is 100. So these two vertical lines, the blue vertical lines, are the two limits. The lower limit for generating unit 2 and the upper limit for generating unit 2. Okay. Similarly, the limit for generating unit 3, let's go and check. For generating unit 3, the lower limit is 0, the upper limit is 50. So again, plot them by the red lines. The colors are simply chosen arbitrarily just to differentiate between the units. Okay, the blue lines correspond to generating unit 2, the red lines correspond to generating unit 3. Then, so 0 is the lower limit for generating unit 3, 50 megawatt is the upper limit for generating unit 3. Okay, so now means what? Means this part of the 2D plane does not belong to my feasible solution space, okay? Because G2 less than 20 or more than 0 is not a feasible solution. So we can't take any solution over here. We can't take any solution lying over there. We can't take any solution lying below this line, or we cannot take any solutions lying above this line. So in short, this intermediate rectangle block over here will give us the feasible solution space. So this is the feasible solution space. In short, I call it FSS. So once we have identified the feasible solution space, now we will try to figure out the solution of ELD. By that, I mean what is the generation for each generating unit and what is the associated cost. So as I said earlier, that if I decide to take G2, G3, and G1, let's say, if I take all the three generating units are participating, because we are not solving, remember, we are not solving the unit commitment problem here. We are considering ELD. So ELD assumes that whatever generating units data are given, all PGs are operating. Okay, none of the PGs are actually inactive here. So all PGIs are active. Okay, so there is no point in considering that, well, I can go for G1 or G2 only, or I will check for G2 and G3 only. No, we don't have any such option available with us because this is not an UC problem. This is rather an ELD problem. So in ELD, we already know that all PGIs are to be taken into consideration. So keeping that in mind, what we will do, we will solve one ELD manually. And that said, it means that we will take as much as possible from G1. Remember, all three units have to be taken into consideration. So because G1 is the least cost unit, we'll take G1 as much as possible. So my demand, remember, is 250 megawatts. So 0, okay, let's start from the other way around. Okay, 0 I can take from the most cost, from the costliest unit. So I will take 0 from G3. Why? Because this is the lower limit, allowable limit for G3. So G3 0 means what? G3 0 means this line, okay, along this line. So the solution is lying along this line somewhere. Okay, next go to G2. So G2 is the next higher cost unit. So I will try to take as minimum as possible. So let's see whether the minimum is a feasible one or not. Okay, the minimum is 20. Okay, let's see 20. So 250 minus 20 is 230. Okay, so it's feasible. Okay, still we can take 230 because 230 is less than PG1 max. So that means it is a feasible solution. I can take 230 and then I can choose 20 and 0 respectively for unit number 2 and unit number 3. So that said, the solution point comes where this is the solution point. Remember, I said G1 is not explicitly appearing here. So we are not plotting G1 coordinate here, only G2 and G3. So what is G2? G2 is 20. So 20 is this point, G2 is 20. And G3 is 0, so G3 is 0 is this line. So this is the G2 equals to 20 line. This is G3 equals to 0 line. This is the intersection. So this is the point of our ED solution in the 2D plane. For the 3 generating unit, we will draw a 2D plane, 1 dimension less. Okay, so now that we have got the ELD, we can easily calculate the cost. What would be the cost? Cost would be summation of beta I PGI. So we know the PGI now. So let's write 230 into the beta I. We'll take the beta I plus for the generating unit 220 plus 0. So it is 0. So we don't have to bother about G3. Only we have to bother about the beta 1 and beta 2. So let's see what is beta 1 and beta 2. So according to our data, beta 1 is 20, beta 2 is 40. So 20 here, 40 there. Let's erase the third one because third one is generating 0 megawatts, so we don't have to bother about that. So this is 4600 plus this is 800. So this will give you $5400 per hour. So this is how we are going to get F00 again means this is our first trial. Because it is a relaxation approach, we have released or relaxed all the possible constraints. Just we are solving the ELD as if no constraints are there. Now, once we have got this generation for each of the generating units, we will go back to the network. This is the network. And we will apply the knowledge of our DC load flow. So let's see how the DC load flow helps us in finding out the line flows now. So if you remember in the DC load flow, we talked about the formulation of Y bus. Okay, I hope you remember what is Y bus. So Y bus is simply the bus admittance matrix, which is a symmetric matrix. Okay, a square matrix, a symmetric matrix takes into account the line parameters only. So using the line parameters, I hope you can build up this Y bus pretty easily. Once we have the Y bus, from that we can find out what is the B matrix. Okay, once we have the B matrix, we can find out what is B dash. This is 1 dimension less. Okay, once we have this, then we can also get what is my B line, small b. Okay, this is a diagonal matrix. All the other entries are 0. So this is B line. And once we find all this out, then this is the node incidence matrix. And along this direction for the node incidence matrix, this is the graph. So using this graph also, we can find out these variables. Okay, so let's say to start with, this is line 1, this is line 2, this is line 3, and line 4. So along this direction, we have the lines. And along this direction, we have the buses. So this is how this matrix is being formed. So now, once we have the lines, so the first line is connecting the bus 1 and bus 2. So bus 1 is there, bus 2 is there, there is no bus 3, so that will take 0 entry. However, there is a direction of sending end bus and receiving end bus. How we will know that? So to know about that, which one is the sending bus or the starting bus, which one is the receiving end bus? Usually, in this case, okay, in this case it's not given, but usually it is given like this. Okay, the line data is given like this: the sending end bus, and receiving end bus. Okay, usually it is given like this. So the sending end bus in this case, let's write it down. 1 for line 1. For line 1, it is 1 and 2. Then again for line 2, it is 1 and 2. For line 3, it is line 3. So line 3 is this one between bus 1 and bus 3. So this is 1 and 3. And line 4 is between bus 2 and 3. So this is 2 and 3. So simply it is 1, 2, 1, 2, 1, 3, and 2, 3. Okay. So means the sending end buses will take the positive entries in the capital A matrix, node incidence matrix, and the receiving end buses will take up the -1 entries. As if the signal is generated from node 1 and it is ending up at node 2. This is the transmitting end, this is the receiving end. So the transmitting end will get the positive signs and the receiving end entries will get the negative signs. So this is how we are going to complete this. If we continue, okay, line number 2 is again between bus 1 and bus 2. Again, sending end bus is number 1, so +1. Receiving end bus is bus number 2, so -1. And bus 3 is absent here. Again, C is the third line, A is the first line, B is the second line, C is the third line. So between bus 1 and 3, bus number 1 is sending end, so positive. Bus number 2 is absent, so 0. Bus number 3 is receiving end, so it is -1. And remaining one is the line number 4, denoted by D with an arrow, means the direction of the flow of information. So this is sending end bus 2. So there is no bus 1 here in line number 4, but we have bus 2. It is the starting bus or the sending end bus 2, and bus 3 is the receiving end bus, so -1. So this is how we are going to end up with this A matrix. Okay, so once we have built all these matrices, okay, so once we have made all these matrices, now we are in a position to move forward to calculate the line flows. Okay, so what are the line flows? So these are the line flows. How we are going to calculate the line flows? Let me repeat the formula. The formula was theta vector or array of theta, except the swing bus theta, because swing bus theta is known beforehand. It is 0, the reference bus angle, reference bus voltage angle. So if it is, because it is a 3 bus system, so we will be only living with theta 2 and theta 3 over here. Then we have the B prime matrix. B prime matrix is basically the reduced version of B matrix. This has been discussed in the DC load flow class. So by now we should know how we are going to get this B prime, and the inverse of that has to be taken, and then the P injected matrix or array, sorry, and that will give me the theta. Okay. So B prime, we have already mentioned how we are going to get the B prime from the B, and B will be obtained from the Y bus. So these are completely interconnected. So this will come like this: Y bus, then B, then B dash. This is the flow of information. Y bus will come from the line data. This is the flow of information. P injection, how we are going to get? Again, P injection means you just draw a summing junction, plus and minus, and this is your P injection for a certain bus. This is your P generation for that bus. This is your P demand for that same bus. So PG minus P demand will give you P injection. So how much is the PG at bus number 2? We got it from here. Bus number 2 will give me 20. What is the demand at bus number 2? It is this. Demand at bus number 2 is 200. Okay. So at bus number 2, I am getting 20 out of my generation, and I am supplying 200 at my local demand. Bus number 3, remember, is 0 generation. the solution of the ELD, but the demand is 50. And bus number 1 is generating 230. So let us see how we are calculating the injection. So the injection is simply at bus number 2, this is my PG2 solution of ELD. This is my P demand at bus 2. This is my PG3 because I'm looking for theta 3. And this is my P demand 3. So PG minus PD, this is the injection. And I have to convert it to per unit. So 100 MVA is my base. So I'm dividing it by the base power so that I have this B prime matrix in per unit. Remember, per unit reactances or per unit admittances. So the power flow or the power injection should be also converted to corresponding per unit values. So that's why we are dividing it by 100. And if I calculate it, then I will get the values in radians. So these are the radian values. And using these radians values, now I can calculate the P line array of information, which is base MVA, because if I want my P line in megawatt, I have to multiply it by 100 MVA base. Then it is B small b, the matrix of B. Then it is A matrix, and then it is the theta. Now here, theta, remember, is of full dimension, means I am including my theta 1 also here. Okay, so you see the theta 1 is over there. This is theta 2 obtained from here. This is theta 3 obtained from here. So this is my updated theta. Now this theta is of dimension equal to the bus number in my network. So it is 3 by 1. Okay, 3 by 1. 3 is the number of buses present in the network. So it is 3 by 1. Here it was 2 by 1. I left out the theta swing bus, theta for the swing bus, because it was 0. We already know it. But now I'm including it because I want to know all the power flow through my network. So once I apply this, I get this information of this much megawatts are being flowing through these different 4 lines of the network. So because of the identical nature of line 1 and line 2, we can observe here that both line 1 and line 2 are carrying equal amount of power, 82 megawatt and 82 megawatt. Line 3, that is P13 flow, it's taking 66 megawatts. Line 4 is taking 16 megawatts. However, there's a negative sign, means, as I said, the convention or the line sending in from receiving end was from bus 2 to bus 3. However, for the solution of this ELD, for this generation mix of 230 megawatt and 20 megawatt and 0 megawatt, for satisfying 250 megawatt of demand, my flow in line 4 is reversed. Okay, it's not a big issue as long as it is within the limits. It is not a big deal. It can happen. So in all the previous first 3 lines, the line flow is following the sequence as it is, like 1 to P12 means the flow is from bus 1 to bus 2. Again, 1-2 means the same. 1-3 means the flow is there from bus 2 bus 3, from bus 1 to bus 3 rather. And P23 means the flow was supposed to be from bus 2 to bus 3. However, because the negative sign, it is flowing now from bus 3 to bus 2. This is the only change that is occurring due to the sign over here. So now with this information, our next step would be to check. Remember, we are following a relaxation approach, so we cannot say that this is the final solution until and unless all the flow over here, all the flows over here are within my permissible limits. So let's check the limits. So when I put the limits on the lines in my network, I see that although line 1 is okay, it is taking 82 megawatts. Line 2 is okay, it is taking 82 megawatts. Line 4 is okay, although in the reverse direction, but it is within the permissible limits of 16 megawatt. However, line 3 is being overloaded. Okay. Okay. Now, how we are checking this? Again, we will go back to the network data, and we'll simply take these values 100, 160, and 80. Okay, 100, 100, 60, and 80. So the first 2 lines are 100, so it is okay. Third line is 60, so now you see it is more than 60. This was 80, but still it is okay, 16 megawatt. So this is the problem now. So the relaxed solution, completely relaxed solution is unable to fulfill all the constraints. So this is not a feasible or a valid solution. So what we will do next, we will redispatch the generations. Okay, we cannot take this could be the most economic solution. This could be, however, this is not possible due to this line flow limit violation. So to correct this line flow limit violation, what we will do next, we will tighten up some of the relaxation, specifically because one of the limits is violated. So we will only tighten up the corresponding limit and we will fix it to a maximum allowed value, that is 60 megawatt. Okay, so in the next lecture, we will see how we are actually going to do this, how we are going to achieve this. Okay, so how we are going to set it to 60. Remember, if we are going to reset this value, reduce this value of 60, then the 6 megawatt, okay, has to be shifted, okay, has to be shifted through some other lines, or this effect will actually, this reduction in line flow limit, of course, will cause some changes in these flows. And that is only possible if we play with these generation injections. So in the next class, we will see that how the change in generations over all, for all these three, any of these three generating units, how this is going to affect my line flows directly. Okay, so this will be, we will be treating it as the generation shift distribution factor, one of the sensitivity factors, linear sensitivity factors, generation shift distribution factor. Okay, generation shift distribution factor means if I am shifting my generation from one generator to another, I'm reducing some generation maybe from here, I'm giving it to there, or I'm giving it to there, or something of this sort. I'm shifting my generation. So generation shift distribution factor, how that is going to affect the distribution of line. Okay, how it is going to affect the line flows, in short. So this will be taken in the next class, inshallah. Okay, so this is where I'm going to stop today. So please go through the lecture because this concept will be applied immediately in the next class for finding out the GSDF, and then with the help of the GSDF, we'll try to redispatch the generations in such a manner that this flow limit violations is being fixed and we get some feasible optimal power flow solution. Okay, so thank you very much, and we stop it here today. Assalamu alaikum wa rahmatullahi wa barakatuh.